Okay, students, let's begin lecture. About homework, we're going to hand out homework in the second half of class. Daniel's still trying to get it all squared away. I just got the Scantrons back from exam 3, and I don't know if anybody has any bloopers on here or not. I think maybe one or two. No, nobody did. Okay. Hey! Bonus points. Nice. You did it. But don't. It's good. You encourage my view of students. That's 2 exams in a row with perfect PIDs and test forms. And I'm not really saying anything bad, right? Because I forget stuff all the time, but it's really rare to get even one exam. You guys have done 2 in a row. Matter of fact, I can't even think of the last time one of my other classes did a midterm or a final. And you know what, guys? Let me give you an admonition here. Concerning the final, and that is, this whole semester, Summer B, has been really, really compact, rush, go. If you mess up the PID or the test form on the exam, oh my goodness. Because we're going to be doing it Thursday, day after tomorrow, 3 o'clock sharp. You can't take the test unless you're on time. If the first student leaves and you arrive after that, it's tough toenails. So get here on time. If you mess up your PID or your test form, or if you don't bubble in correctly, or if you don't bubble it in properly, it's going to be rough getting your grades in. And if you're all right, who's supposed to be graduating? Sweet. So hopefully that'll take place, and you can go on. And congratulations. I've been seeing people taking graduation photos. I just saw somebody in the student union, a bunch of little balloons that said 2. One said 2, another one said 0, another one said 1, and then one said 8. And it's sparkly and silvery, and I was trying to photobomb them on my way through, but All right, here's our. This is an easy week. Today's formulas are going to be cinchy. We're going to talk about the quantum theory of matter. And the theory of photons and stuff, the quantum theory of light is also pretty easy. So let's get down to business. Question? Is the final going to have a mapping section with formulas like our other? It'll be just like a midterm. So there'll be some matching, probably some true or false, maybe, multiple choice. And the multiple choice will be concepts and or calculations. So it's double the size of a midterm. And unfortunately, since it's summer, we only have 2 hours. Now, normally, final during the regular semester, you get 3 hours. 2 hours and 50 minutes. But this one, I think you guys should be able to hack it, but you're just going to have to work, with dispatch. Question? Previously written out solutions for questions on the final. I thought I did post at least one of those in Talking PDF. My Talking PDF is kaput. Or I got to reboot it or something. I don't know. It's not working. Keeps crashing. But I did post the test key for your guys' test forms for exam 3. But, you know, Tatiana, probably not, because, between now and Thursday at 3 p.m., and you guys, you may hear on the news of a raving maniac wandering Orlando with a computer under his arm. That would probably be me between tomorrow 5 p.m. when we dismiss and Thursday 3 p.m. when we convene again for the final. I'm just going to be but office hours tomorrow is going to be good. So we'll have that, and hopefully things will go good. All right, let's keep going, and we're talking about quantum electrodynamics, also known as QED. Now, this is not in your textbook, so take good notes. I'll ask you questions about this on the final. And we're not going to do any ginormous calculations, but I am going to show you some diagrams that are important. QED, quantum electrodynamics, is the first of the fully quantized field theories in physics, and it is the quantum field theory of the electromagnetic interaction, quantum electrodynamics. Now, the thing about it is, it's actually modeled on diagrams like this. Not fancy, I shouldn't say not fancy calculus. This diagram here, it looks like a stick figure. It's an electron coming in from the bottom and an electron going out towards the upper left, and a squiggly there to represent a photon. By the way, that kind of squiggly looking symbol here above the green squiggle, this one right here, that's a lowercase Greek letter gamma, which is the traditional symbol for a photon. And believe it or not, this diagram represents some monstrous calculus equations, but it all works. And this is a diagram of a photon interacting with an electron, or an electron interacting with a photon. You can make a similar diagram for a positron, which is the antimatter version of the electron. And as I've mentioned before, antimatter is a thing. It is not science fiction, it is science. We have guys all over the USA working with antimatter every day. It's not easy to work with. Small amounts, though, yeah, we got it. Question?
So, antimatter is basically like the other position for matter, or
Antimatter is not a position. Antimatter is a different state of matter, and whatever. We happen to live in a part of the universe that's all regular matter. Protons are positive, electrons are negative, neutrons are neutral. But antimatter, protons have the same mass but a negative charge. That's an antiproton. An anti-electron, also known as a positron, same mass as the electron, but positive charge. And here's the interesting thing. When the electron and the positron collide, they annihilate each other. And they produce a pair of photons, outgoing photons. And so it's definitely a high energy interaction. So it's a real thing. There's even an anti-neutron. An anti-neutron, is an antiparticle. And so all the basic particles of matter have an antimatter component, or a matching state. Same mass, opposite charge in the case of the electron. And the interesting thing, and this is why I bring it up, it's modeled in the same way, except a positron moving forward in time, like here's an electron moving forward in time from the bottom of the screen to the top of the screen, okay? A positron is modeled as an electron moving backwards in time. It works out perfectly. So time reversal in the diagram, and you're talking about a positron, and I'll give you an example of that in a minute. Now, another quantum field theory that we've got a good solid handle on is something I've mentioned before, and that's the electroweak theory. I'll talk to you about that tomorrow when we talk about nuclear radiation. Question?
If the nature of antimatter is like they have the same mass but different charge, you said there's an anti-particle for the neutron, but the neutron doesn't have a charge. What is the charge?
That's right. They still annihilate. Become a physics major. There's a lot to learn, and there's a lot of stuff that we still don't know the answer to. Okay, for instance, why don't we have more in our neighborhood of the universe? Why don't we have more antimatter? Why is it so hard to find? Why do we have to make it in the lab, which is what we do? You know, and we know that in the center of the sun, all these big nuclear fusion reactions in the sun, there's a lot of antimatter activity going on in there, but it's with antimatter, there's a lot of mysterious things. Now, electroweak theory is also a quantum field theory, but it involves nuclear radioactive decay. So a proton and a neutron, they decay into the other through the emission of electrons and anti-electrons. And I'll go over some diagrams for that with you tomorrow when we talk about radioactive decay. And by the way, tomorrow we'll have the first half of the lecture will be a regular lecture, probably on nuclear radioactive decay, the stuff I outlined yesterday or that I listed yesterday. And then the second half of lecture, maybe the last 45 minutes, 30 minutes, we'll have a little review using iClicker like we do on exams. It'll be self-paced. And you'll work with your neighbor and just work on problems together. And that'll be a little review, kind of a dress rehearsal for the final exam. And I might have 10 or 15 questions, so I'll give everybody a handout, and you'll click answers in with your clicker. And that'll be the last 45 minutes, half hour for tomorrow. So, by way of a little bit of prep. Now let's do a basic quantum electrodynamics diagram together. Here's the first feature of a quantum electrodynamics diagram is this, that the time axis is on the vertical. Okay, and I've got it sketched out down here. And the spatial axis is horizontal. Okay, so the x-axis goes that way. Time axis goes up this way. And write it down as CT, speed of light times time. And that way, both axes are measuring centimeters and meters and stuff. What it's like is having your distance scales in light years. Light years is speed of light times a year. That's the distance. A light second is speed of light times a second. We've got about 500 light seconds between the surface of the sun and our planet. It's about 8 minutes, 8 light seconds. That's how much time it takes light to get to us. All right? The outer solar system is a little bit Pluto and Neptune and stuff like that. They're a little further out. But they measure that in light minutes as well. All right, so that's the first thing. So increasing time, later time, normal motion is vertical, upward, and positive x is rightward. So if you're moving to the right, you're slanting up and to the right. If you're slanting up and to the left, that means you're moving to the left. Okay? Now, go ahead and draw this diagram again. This is what we call a primitive vertex, a primitive stick figure. And in this diagram, the steepness of the electron lines corresponds to the speed, but not directly. It corresponds inversely. So one of the things that we've talked about and you've seen in lecture is the relativistic term beta. In terms of the speed of light, beta is equal to whatever speed you are divided by the speed of light. So beta is a rating of your speed in units of the speed of light. Now, the speed of light is something that physical objects other than photons cannot attain. So everybody, for any physical object like you or your car or an electron or a proton or a neutron, they're all going to be somewhere between 0 and 0.99999. And we can get protons way up there, electrons too. We can get them up there to 4, 5, 9s. But nothing can get up to exactly 1 times 100% of the speed of light except light itself. All right. Now the angle of tilt, in this case, these are 80-degree lines. So this one down here to start is tilted 80 degrees above the x-axis. All right, and you can look up the tangent for that. The tangent is the rise over the run for this line. And here's one that's tilted back. So this one's 100 degrees. So it starts at 0, goes to 90, and then another 10. In other words, it's 80 degrees above the negative x-axis. So it's 80 degrees this way. All right? And so what that models is a photon that's kind of moseyed along at a certain speed, and it works out that this is about 18%, 17.6% of the speed of light. So if you get an electron, that's good, that's booking pretty good. I mean, that's a good speed for an electron. I mean, it's a good speed for anything. Well, we can get electrons up that fast. It's not that hard. Now it's not. 100 years ago, it would have been kind of a nice conclusion, but now we just, it's easier than walking through the park for a scientist anyways. So if you're going at 17.6% of the speed of light on a diagram of this kind, on a QED diagram, that's your tilt angle. If you're going 0.176C to the right, then you have that first tilt angle up here at 80 degrees. If you're going to the left, and so let me ask you a question. We have an electron in the lower half of this diagram that's traveling speed of at 17.6% of the speed of light to the right. And in the upper diagram, it emits a photon off to the right. And then it's now heading left 17.6% of the speed of light. What words would you use to describe the state of motion of that electron? The electron blank. Raise your hand. What do you think, Asia?
Kind of like the electron refraction.
That's a lovely thought. It does look like an electron diffracting, doesn't it? It changes direction. Please send me a message in web courses. I want to remember that. Except this is a particle diagram, so not a wave, but it is reminiscent of diffraction. What else? Who else has got an idea? Were you raising your hand, or were you just scratching your? Okay. Who else has got an idea? Okay, Lyle. bouncing. Yeah, okay. Yeah, it goes right, goes left. It emits a photon, changes.
If it's changing like direction, maybe it's a positron now?
No, it's not a positron, it's still an electron. This is an electron diagram, but it is changing direction. Okay, let's keep going. Now, this thing here, whoa, I just jiggled the cable, sorry. This one up here, the squiggly, the green squiggly, is a photon. And you see different ways of graphing up a photon. Sometimes you always see photons at 45 degree angles. Because in this kind of a diagram, this is a space-time diagram, and in a space-time diagram, photons always go at 45 degree angles. Anyways, we got this one here, and we call it a virtual photon, and this is the means by which the Coulomb interaction is changes the momentum states. Okay, we think of electrons and protons as repelling or attracting and stuff like that. This is in quantum electrodynamics. This is how you represent that. But the thing is, we don't have an interaction yet. We got to put some more stick figures in here. This is just one electron. Okay, an electron, if it doesn't have something else to interact with, it's just going to keep going straight. It's not going to cut back to the left. So we got to do some stick figures with these two rays and arrows, and then we'll have a full interaction. All right? Now, a minute ago, I asked you, well, how would you describe the dynamical state of this electron? It's going right, then it cuts left, and somebody said it bounces, and Asia said, well, it's kind of diffracting, and Jade said it's, what did you say, Jade? Okay. But what we're doing is when we put the other electron in, we're going to have an exchange of momentum. And that means that there's an acceleration. Jade, you mentioned it changes direction. And how do you change a direction? Even if the kinetic energy is the same, you change the direction, you have to have some kind of a force. Delta P over delta T. All right? And that is, now we represent the exchange of momentum with that photon. And I want you to do a mental picture, if you will. I want you to think, and this is something I do with all my classes, but I forgot to do it this semester. And it's really for Physics 1. But if you take two people on skateboards, and they're at rest, and they're facing each other, and if one of them has a medicine ball, so a little bit of mass, and he hefts it over to the other guy, and the other guy catches it, what happens to the other guy? He goes rolling off in that direction. All right. Now, if he throws it back to the first guy, and the first guy catches it, what happens to him? He rolls off the other way too. So that is how you can model two skateboarders exchanging a medicine ball. And what we're going to do in here is put another electron. So let's get down to it. All right, this thing's accelerating, but right now there's nothing to accelerate off. Here we come. All right, now here's my construction. So here are my Legos over here to the right. All right, and we got these arrows. And believe me, you can make some really complicated diagrams with these basic Legos. Here we go. First one, let's put one up here. Okay, there's the outgoing electron after the interaction, and it's cutting over to the right. Now here's the incoming. Zip. And what happens to these babies? One's coming to the right, one's coming to the left. They exchange a virtual photon, and now they're going back the opposite direction. What do you call that? It's a force. what did the electrons do? They accelerated. What's the one word we have for electrons that do this? What? They repel. Ding. All right, so here's your, there's your electrons. Go ahead and label them. So this is two electrons interacting. They reverse course and they skedaddle on out of there. They hightail it out at 18% of the speed of light. Through the exchange, not of a medicine ball, but of a virtual photon. Okay. Now, this, my wonderful, go make a new diagram, same shape, but notice these are arrows now. And they're going downwards. These are electrons going backwards in time, or two positrons, the antimatter partner of a regular electron. Same mass, opposite charge. So when I say that we model a positron, which we know exists, we know that they exist, we've measured them in the lab. We can even make atoms with positrons orbiting a negative ion, positronium they call it. So we know that positrons exist. How do we model them? Ding, just like this. And, there's other diagrams that you can make with positrons. This is, like about the most basic one. And this is positrons repelling. All right? Now, I want to draw your attention to something else in this. This diagram, and this is all I want to show you about quantum electrodynamics. This diagram. And this one's the positron diagram. You can think about the electron diagram that's similar to this. It is a mixture of something that we think of as a wave, the photon, and two particles, the electrons. So what is up with that? This quantum electrodynamics was invented in the middle 1900s, about 1948. And the quantum theory was begun about 50 years before that, in about 1898. And so that's what we're going to now study. First, we're going to put in place the quantum theory of light, the middle part here, and that'll give us a flavor of what's going on in this middle part, the mediation part of the QED diagram. And then we'll talk about the quantum theory of matter. And that'll be for the two blue trajectories, the one on the left and the one on the right. So, quantum theory of light. And as I alluded to at the end of class yesterday, this is the story of Max Planck, who came up with this quantum theory of light and a constant called Planck's constant. He didn't call it that. But he came up with this constant H, and it turns out to be the one constant that rules over every dynamical interaction, galaxies, electrons, and everything in between. Now, what was he thinking of? 120 years ago, 1898, 1899, in there. He was trying to figure out this. And this is a diagram from your textbook. These are called Blackbody spectra, or Blackbody power radiation curves. And the way that you look at this is these are the vertical scale is the intensity. The horizontal scale is increasing wavelength. So what scientists were doing in the late 1800s, they had incandescent light sources. And they had diffraction gratings and prisms. And so what they did, they broke up the light from their, they set the temperature, And then they broke up the light and measured every color, the amount of energy in each shade of red, each shade of orange, each shade of yellow. You know, and they could go, and this one, you know, it says down here per unit wavelength. So nanometer by nanometer, we do it now. Okay? And so what they found was that if you look at an incandescent light source, something that's emitting light, like these light bulbs, because it is hot, it has a distinctive distribution of energy. And this is what we call the Blackbody Spectrum. Now, what is the term Blackbody? Blackbody is a reference to this theoretical construct. An object that's black is black because it doesn't reflect any light towards your eyes. Okay? You shine a light on it, it's still black. And that means it's a perfect absorber. But if you heat it up, it will glow. Okay? And so the black body is our kind of idealized construct. The theoretical object that is a perfect emitter and a perfect absorber of electromagnetic radiation. Let me repeat that for your notes. A black body is a theoretical construct. And I don't think Max Planck didn't invent it. Black body, the theoretical construct that is a perfect emitter and a perfect absorber. And what scientists did was, all right, like the filament of a light bulb, it emits light because it is hot. Now, it's not a black body, but it's pretty close to a black body. And what they found was that the hotter it got, there were still colors of light. Now, down here's infrared. They expected to get more infrared. You know, the more energy you pump into it, you ought to get more infrared. But that wasn't the case. They found that there's a peak, and you start out with, now down here, this is ultraviolet down here in X-rays. Really small wavelengths down here. So they can measure some of these, but they don't get a lot. You know, so you rev it up to, 1.21 gigawatts, and you still don't get, an untold number of photons out of there. It still curves back down. So this bump, this is what we call a blackbody spectrum, a bump. Nobody knew what it was. Nobody knew why it was there. I mean, the F equals ma of the black body, people could figure out, okay, why does it rise from the short wavelengths? They could figure out the left side of this. And they could figure out the right side, it's going to taper off with longer wavelengths. But they couldn't figure out a single theory that rose from the long wavelengths, came to a peak, and then dipped back down to the short wavelengths. They couldn't get it, except for Max Planck. He's the one that figured it out. Now, this 6,000 Kelvin, did you guys have the Kelvin scale in Physics 1? Raise your hand if you had Kelvin scale in Physics 1. 1. Who had Kelvin scale in chemistry? Okay. Oh boy. Kelvin scale, it's a metric temperature scale. It starts at absolute zero. It's Celsius minus it's Celsius plus 273. All right, so 0 degrees, freezing point of water, Celsius is 273 Kelvin. And otherwise it matches Kelvin for Kelvin, Celsius degree for Celsius degree. Anyways, the Kelvin temperature scale is what we use for thermodynamics. This is thermodynamics, the blackbody spectrum. Now, our star, the sun, the surface, the photosphere of the sun is about 5,800, 6,000 Kelvin, rounded off here. All right? And this power curve, this spectrum, shows you, for Risa, that the sun puts out most of its power in the visible. That's where the bump is for the SUN. Now, if you have a cooler star, like Arcturus, 4,000 Kelvin, it's going to have a peak. What color is Arcturus going to look like? It's going to be red, because the peak is down in the about 700 nanometers, all right? So when we look at a star, this is amazing. When we look at a star and we figure out its peak wavelength, we automatically know the surface temperature. It's pretty cool, just looking at it. And you know where humans are? We're at, like maybe 300 Kelvin or 300, I don't know, what's body temperature, 310, something like that. So our peak is really low. We don't put out a lot of infrared, but we're down here in the infrared. Our peak is down here in the infrared. That's why night vision goggles use infrared. If you want to see somebody in the night, and if it's 98 degrees out, you can't see jack. I mean, somebody can be walking right in front of your nose and you won't see him because everything's 98 degrees. Right? But if it's 80 degrees or 70 or cooler, like out in the desert, it gets really cold at night, yeah, you can pick up humans like nobody's business. And it's down here. All right? So these are the Blackbody spectra. And nobody could figure them out until Planck said, okay, my wonderful students, let's assume that all those atoms in the black body itself, they're oscillating and they're, accelerating, emitting light. Let's assume that they only emit light in bundles of energy proportional to the frequency. So if they're at a certain frequency, the energy that they emit is proportional to that frequency. So that's this formula here, equals HF. And if you have 1,000 of them at that frequency, you just multiply this by 1,000. Right now, this is one of the formulas in your chapter 29. Question? Yeah, so you're looking at the book. Yeah, there's an N in the formula in the book near this diagram, and that stands for how many oscillators you have at that temperature, at that frequency. Okay? But one of them is going to have energy at this magnitude. Now, Planck is the one, he said, because the people that could figure out the left-hand side of this spectrum, they were thinking F equals ma, continuous energy distribution, and they couldn't make it bend around and dip back down to zero. The guys that could figure out the right-hand side over here, long wavelength, they could get it to rise, but it just kept on rising. Their theory, they couldn't get it to bend back down to zero. But nature bends it back down to zero. And Max Planck is the one that figured out how to do it by quantizing the oscillator's energy in bundles of HF. And H, that's his constant. And he figured it out. And by God, it all worked. But you know what? It involves extremely fancy statistical methods and exponentials. And Patrick, the thing about it is, you have to look at this diagram and this set of notes here, Patrick Blanchett, welcome. You're nodding off there a little bit. That's all right. I know. When I was an undergraduate, I would sit in the very front row, and the classes right out. I would go swimming at the law school during lunch sometimes, 3 times a week. And I'd get to class right after lunch, and the first thing that happened, fall asleep. So and my professor, he didn't give me the business. Oh no, one of them did, because I was in this physics class, and I started snoring. And no, it's worse than that. It was so loud, I woke myself up. And I looked around the class, and my professor's up there, you know, at the chalkboard thinking, what an idiot, you know, and all my buddies are giving me the business. Anyway, Planck's. So Planck's constant. So Planck made this, you know, this exponential function, e to the bunch of stuff. They're really complicated. And it, you know, the F equals ma, conservation of energy, conservation of momentum, conservation of angular momentum, this and that. None of it made sense until he used this constant. There it is. In joules, regular metric, joule seconds, 6.626070040 times 10 to the minus 34 joule seconds. Now, my wonderful students, if you had anything about angular momentum in physics 1, a joule second is the same, and you go ahead and write this down, kilogram meter squared per second. A joule second is a kilogram meter squared per second. And that will be handy in calculations when you're trying to figure out a distance, you know, a wavelength and stuff. And we're going to be doing wavelength calculations here in a second. All right? Now, in terms of electron volts, it's 4.135667662 times 10 to the minus 15 electron volts seconds. All right, so that one, that unit for H, for Planck's constant, is just about the right size for atomic systems. It's pretty good. And there's a difference. Notice the difference in the exponents? 10 to the minus 34, 10 to the minus 15. 34 minus 15 is 19. Yeah, the charge on the electron. That's all this is. 1.602 times 10 to the minus 19. Question? Same as the ratio between an electron volt and a joule.
Just to clarify from the graph we were looking at before of radiation intensity per unit wavelength, is radiation intensity like
Just
synonymous with temperature?
no,
Okay, but is it
but they're directly related.
so that
Jade. Career advice time. Become a physics major. That's the only way you're going to get to the bottom of these questions. Seriously, because that's an enormous question. You just like what Asia said, you know. Now, on a human scale, this is an important concept. Joules and seconds, that's human scale, you know, kilogram meter per second, meter squared per second squared. That's kinetic energy of something. Half a kilogram going 1 meter per second. Basic. No, 2 kilograms going 1 meter per second. Very basic. 2 liter bottles of water. It's extremely small. On the atomic and nuclear scale, if you think about it in terms of electron volts, you know, electron volts is the energy unit that you want for atoms and molecules and stuff usually. I mean, you can do everything in joules. You know, you can do everything in foot-pounds. That's the English system, you know, human scale energy measurement. You know, some people still use foot-pounds for energy, but atomic scale, electron volts and seconds is good, and it's pretty good. And we're going to do an example of de Broglie wavelengths here in just a few minutes that brings that out. All right. And so that's where we're heading. Now, Planck's constant is also known as the quantum of action. And action is a really fancy calculation like potential energy, only it's really fancy. And it has units of joule second, kilogram meter squared per second. So Planck's constant is the quantum of action. And about 110 years ago, Planck came up with this theory, and it looked really good. And then about 113 years ago, people were still trying to figure out, okay, we know these energy levels around the atom, they have to be quantized, n equals 1, n equals 2, n equals 3. But how does nature, why does nature quantize itself? Why does it say only certain orbital sizes are allowed and no other? Why does nature insist on quantum leaps in atoms? Now, we don't do quantum leaps except on that one television show from the 80s or whatever it was. Humans don't do quantum leaps, but atoms do it all. The atoms are doing quantum leaps as we speak. Every atom in your earlobe is doing quantum leaps. Jade. It's a leap from one allowed. You guys don't know what a quantum leap is? A quantum leap, it's all right, I'll explain it. A quantum leap is what electrons do around an atom, and we now use it in a generic sense, but originally, Niels Bohr, the guy that figured out this model of the atom, the hydrogen atom, he said an electron can make a jump from one orbit only to a set of countable orbits below it. So it can't go from n equals 3 down to n equals 2.5. Only those specific altitudes are allowed. So it can make jumps of a certain size and no other. And the certain size is, as we'll see, is controlled by Planck's constant and the electromagnetic interaction between the proton and the electron. Okay? And it all has to do with electrical potential energy and photons and stuff. Question?
It's like sort of like discrete movement from one place to another.
Yeah.
Like it kind of flowing.
It's kind of like chess, like a pawn can only go, after the first move, it can only go in one step forward, okay? Or it can take one step diagonally when it captures another player. That's quantized. The knight is quantized. The other ones, they're kind of quantized by direction. The queen's not quantized by direction. It could go in any direction. But the bishops only on diagonals, the rooks only on squares, only straight up and straight across. And the king is quantized. He can go in any direction, but only one step at a time. So why does nature do that? Well, the guy that figured it out is this guy, Louis de Broglie. Kind of an interesting guy. He was a soldier in World War II, and he never made it out of Paris. He was some kind of a genius. So they said, well, we better not send him up to the front, where the machine guns are. So he was operating some radio transmitter in the Eiffel Tower or something like that. So he's bored out of his mind during World War I. And then after the World War I, he buckled down in grad school. His PhD thesis was this: why not treat an electron as if it's a wave? All right? And who would ever have thought of that? Everybody thought electron, it's a particle. All the scientists up to that point. It's about 1923 when he published it. And they sent his thesis to Albert Einstein. And they said, this thing is wild. Let's send it to Professor Einstein. We got to find out why it's wrong. And Einstein said, this thing is the cat's meow, man. This thing is great. He said, this is fundamental. And it was. If an electron is a particle, how can it also be a wave? That's like saying that you have a bookcase, everything's squared away, just like a particle. You got shelves, you put something on the shelf, it's there, it's nowhere, you know where it is. It's like saying you have a bookcase that's also a horse. I mean, it's, but that's what de Broglie thought, So So Asia, here's the question. Will electrons diffract? Now, I've already, tipped you off. I mean, the what do they call those things? The spoiler? I already gave you the spoiler on this. Yeah, they do diffract. Particles ain't supposed to do that. They're supposed to go straight through the gap. Or they're supposed to get stuck at the barrier. And de Broglie said, oh no, my friend. My buddy Albert Einstein and I, we know this stuff. If you model the electron as a wave, it will, and if you assume it has wave properties as well as particle properties, if you assume it's a bookcase and a horse at the same time, then the hydrogen atom, bing, it all works. Now, before we get to the hydrogen atom and how it all works together, about the time that he came up with this theory and his thesis cleared and they published it, there were some guys in America that were blitzing electrons into nickel crystals of nickel. And a crystal has a regular spacing. That's what it means to be a crystal. So it's like a set of diffraction barriers. And they were blazing those things in there, and they said, whoa, that's what this is. We are getting diffraction patterns. Okay, now this is what it looks like if you have a bunch of crystals that aren't all oriented the same direction. You get, instead of getting dots in certain directions, if they're all discombobulated stuff, you get a set of dots as circles, and that's what those are. All right? And this image here is aluminum crystals. Now here's their original paper. See that? December of 1927. One of the most famous physics papers of all time. Diffraction of electrons by a crystal of nickel. The horse, the bookcase that is also a horse. They saw it. They saw the electron diffract. They measured it. And here's a pull quote. I've got it outlined in red here. Here's what it says. I'll blow it up for you. Now look at this. This is an important sentence. Equivalent wavelengths of the electron beam may be calculated from the diffraction data. They measured it on the screen. They looked at the diffraction pattern. They measured the radii of those circles. And they say in the usual way. So they knew how to do it. Everybody knew how to do that with diffraction data. I mean, they knew how to do it with X-rays. But these are electrons. These turn out to be an acceptable agreement with the values of what? H over mv. What is mv? Momentum. And H, that's Planck's constant. So they're saying here, dude, we got this diffraction pattern, and it squares perfectly with what de Broglie hypothesized. Undulatory mechanics. That's the old-fashioned word for quantum mechanics, wave mechanics. Here is his formula. This is the de Broglie relation. The wavelength is equal to h over p. They could set the momentum, and here's how they set the momentum. Velocity selector. We know how to do that. And then they measure the diffraction pattern on the wall out there on the screen, with their meter stick and their measuring tools. And they get lambda. They figure out theta and they figure out lambda. And by God, it all worked. And so, hold on, Windows is about to log off here. All right. So what we're going to do now, go ahead and write that equation down, the de Broglie relation. We are going to calculate on the document CAM. 2 examples, and then you're going to do one on iClicker. So have your iClicker handy. All right? And let's get ready to. So let me pause the podcast. Excuse me, pause the YouTube. Okay, so we just did those examples. Let's do a clicker question. Okay, turn on your unit, hit the refresh key, you're going to get I want numbers now. Here we go. Calculate the de Broglie wavelength of an electron moving at 18% of the speed of light. Hit the refresh. Let me see your device. Yeah, let me see. Oh, it's got, I didn't start it, sorry.
Oh.
Okay, you got it now? Okay.
These, I think this was supposed to be your pilots, okay? These don't have names or
Somebody gave in a paper without names. Oh, this is Bernard. 2 people without names here. I'll deal with those later. Doing a de Broglie wavelength. Doing a de Broglie wavelength calculation.
do they get quantum mechanics stuff in this class?
Dude, I just showed them QED.
Yeah.
They're experts on it. Some of them have some really good questions. Really, actually. This is old for me. Okay, I want A through L. No, I have, this is the old stuff. This is the stuff.
H through.
Oh, do you have the exams for this?
I'm grabbing them right after this. I've been stuff all morning.
Yeah, it's good.
I can sneak in and drop them off on my way back.
Yeah, I have G through L, so give me A through F and A through G. Okay, good. But we're not quite ready. So we're just doing a calculation, then we'll finish after that. I want, round off carefully. I can see some good answers, but I can see some people that aren't rounding off properly. Work with your scientific notation. seconds.
Double check. Be careful how you round off. Thirty seconds. Don't forget to hit the send key, otherwise it won't. Take your number. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Appreciate it if you got that. Nice. And hey, you guys, just for the conversation, yeah, we got a lot of damage here. You're in the right ballpark, but you're not adding, you're not rounding off properly. So, see that? Look at all these. Okay, this one looks a little off. But all these are, well, that one's not right. So, you guys, when you're doing a if you have to do a calculation like this on the final, round off carefully. Question. What's that? No. No, you have to have this on the money. I asked for it very carefully. Okay, let's go back to the YouTube. All right, so there's your answer. Now, here's the. Here's the. Yes, question. What? Yeah. What? I can't hear you, and I'm not. No, that's what I asked for, and I didn't ask for 0.014 or 0.012. You got to get it on the money. I mean, we're trying to save lives here, right? Aren't you guys in med school? I mean, trying to get in med school and save lives. You don't want to be 10% off, because 10% off means they're dead. All right, but no. All right.
Based off of the map alone, wouldn't it have been easy? Like, I know that you wanted to, and that's fine. But
Yeah, possibly. But the reason I do it with a clicker is we have to be able to grade it. Okay, so that's why we do that. That's why I always specify what I want. All right, so we just calculated some de Broglie wavelengths. Now this is de Broglie's vision. He said that an electron on orbit will find an orbit, so a certain radius, certain altitude above the nucleus, in which it forms a standing wave. So constructive interference all the way around. The electron is interfering with itself constructively. And if it doesn't interfere constructively, you won't find it. And this is how the orbits, and it works beautifully for the hydrogen atom. It all works out really, really sweet. So, Niels Bohr came up with basically thinking of electrons as little planets orbiting the nucleus. But nobody knew why they only assumed certain orbits. This explains why. Because only certain distances, and because it's a certain distance from a particular charge, the potential energy. So you get everything. You get the energy of each level. You get delta energy between each level. And because the energy of a photon is equal to HF, the frequency of the photon. And that is how you figure out the colors and the energy levels of hydrogen. There it is. There's the spectrum of hydrogen. It works out great. Really great. So H and delta EPE, select the orbital size if it's a wave. Constructive interference. It's kind of weird, a particle interfering with itself. But that's how we model it. And then the orbital size, that controls the photon, because the photon is emitted when you make a quantum leap from a higher orbit down to a lower orbit. Okay, so that means, and that energy, that delta EPE goes into HF. All right? And it all worked. The hydrogen atom, bing, they got it. Now, helium is a little tougher. And forget about, the big atoms like gold and uranium and stuff, they're really tough. But, hydrogen is the simplest of them all, and we got it. 90 years ago. Question?
What about, well, I guess maybe this would be included in other, for larger atoms then, but like, when you have orbitals that have more than one electron in them, like, I know they're opposite spins, so
You still, what you do is you look at the diffraction line, you look at the spectrum. This is a discrete spectrum. Certain colors only. For neon, it's really complicated because that's a bigger atom. But if you analyze all the wavelengths in that spectrum, it corresponds to a quantum jump from one level down to a lower level. Okay, and so you work out all the, HF, and you figure out the nucleus, the charge on the nucleus. So for neon, it's 10. So you figure out delta E. So you can figure out everything, except it gets a little more complicated for the bigger atoms. But for hydrogen, it works like a charm.
it doesn't
Okay.
work like a charm because there's not more than one electron that you're
Yeah, it's the simplest. So the mathematics for the bigger atoms is more complicated. All right? But it happens, this picture back here, it works out really nicely. It's a very good explanation for hydrogen. But the electrons above hydrogen are a little bit, helium's not too bad. So electron diffraction. Check this out. I don't even know what you call it. I think this is a dodecahedron, which is a crystal mode. And you zap those electrons through there, and you can see different patterns. And if you take a different angle, look at the same crystal, but the pictures on the right in blue show you the different angle that you're aiming your electrons through. So one's going in right down the pipe where it looks like a pentagon. And this one is, you're aiming through an equilateral triangle. This one, you're kind of, the lowest one, you're aiming through a pair of equilateral triangles that are kind of slanted away from you. All right? And analyzing all those dots stuff, tell you the structure. Of course, here's the very famous image 51. And then this is of course, this is X-ray diffraction, not electron diffraction. But you can, here's an image from your textbook. Neutrons diffracting through NaCl, sodium chloride, cubic. All right? And so one of them on the left is, the one on the left is neutrons. And so neutrons have wave properties too. You know, we can pick that up. And then, see that central image? See that bright central image? Yeah, the central fringe, as we were talking about yesterday. And then you don't really, and then this one over here on the right, that's X-rays. You don't really get jack over here. Everything gets, you know, messed up in the middle there. But you get all kinds of diffraction patterns. You analyze those, you figure out the structure that you've got. All right. Last thing I want to mention before we hand out papers is final exam is Thursday, day after tomorrow at 3 till 5 o'clock, and you got to be here on time. All right, I have A through L. I'll start with the A's. Farisa. Daniel, go ahead.
I have M through 0.